So let us now take a look at a couple of practice problems related to the concept of present values, annuities, and perpetuities. In the first problem, we are going to actually figure out a way of deriving the formula for the perpetuity and for the annuity without resorting to using the formula for the sum of finite or infinite GP series. We want to just use finance principles to kind of see if we can come up with an expression for those formulas. And in the second one, we'll see how the concept of no arbitrage pricing that we had discussed, that can be used to think about how depletable resources such as oil can be priced. Okay, so let us start with the first problem. So you have got actually two students, A and B, who are very bright in terms of knowledge of finance, but they unfortunately do not remember basic high school mathematics formula, particularly related to how to think about how to sum up GP series. Okay, so they are trying to combine their knowledge to come up with how to actually get the formula for perpetuity without using GP series. So you have got basically student A who's trying to figure out the formula for the present value of a stream of payments of 1 unit a year, beginning 1 year from now and continuing forever, right? So this is the basic perpetuity, if you recall your definition of perpetuity. So he's aware that the interest rate is going to be remaining constant at R forever. And he also knows that this value is expressed by this following infinite series, right? So as I said, he's aware of the concept of finance, and so therefore he knows present value, right? So he knows that the present value of a stream of payments of 1 unit a year beginning from 1 year onwards has to be calculated in the following way. So 1 year that is coming up is 1 unit that is coming up 1 year from now. That discounted in today's terms means it is 1 by 1 plus R. The 1 unit that is coming up in year 2, if you discount it in today's terms, it means 1 by 1 plus R square and so on, right? So he's aware that this is the sum that he needs to calculate. The only issue, as we mentioned, is that he does not know how to find the sum of infinite geometric series. So he has to rely on his knowledge of finance and common sense. Okay. So for example, he's aware that if instead of beginning 1 year from now, the amount of money actually started from today itself, right? Then the present value of this sum would be 1 unit higher, right? How does he know that? Well, he knows it because of two different reasons. One, he knows that the present value of getting 1 today is 1 itself. So basically, once I'm calculating the present value, I just need to add 1 if this 1 is beginning from today rather than from 1 year later. And the second thing is he also sees that, if he is adding 1 to both sides, he basically ends up getting this, assuming these things are finite, which he knows it is finite, right? Okay. So this is where he is, but he needs more help, right? Because this isn't enough to kind of solve for P in terms of R. So he approaches his friend student B, who also does not remember the formula for the sum of geometric series, but the student B also kind of like has been paying attention to finance classes, and student B is aware that the present value of 1 unit a year forever, starting now, has to be at least 1 plus R times as large as the present value of 1 unit a year starting 1 year from now, right? So this is basically, he's comparing the two present value if you were to begin today versus if you were to begin from 1 year down the line. So this has to be related by a factor of 1 plus R, right? So this is again going back to the basic notion of present value, okay? So the question is, can student A and B combine their knowledge to get an expression for P in terms of R? So let's see what we have. So based on what student B knows, basically what he's saying is that if the money had started today, so that means that you have got 1 today plus 1 by 1 plus R. So that is the next period and so on. And if you add them all up, and if you want to compare it with what would have happened if the money was starting 1 year in the future, which we already know is denoted by P. So then these two things are related by 1 plus 1 by 1 plus R and so on has to be equal to 1 plus R times P. Okay. Again, so based on this is this kind of like going to be enough? By the way, this is something that you can also see from here, right? If you were, instead of adding 1, if you had multiplied by 1 plus R, this is exactly what you end up getting, right? So again, these are things that you could have also seen from basic algebra without kind of like knowing the finance thing. But let's see how they put this knowledge together. So how can like the combined knowledge of A and B help to solve the problem? Well, this expression that you see on the left-hand side, 1 plus 1 by R, so on, A already had an expression for that, right? That was P plus A, 1. And B, based on his knowledge, knows that this is equal to 1 plus R times P, right? So now if you combine the two, what you get is P plus 1 is equal to 1 plus R times P. And this you can actually solve for P in terms of R, right? So this P and 1 into P will cancel out. So you end up basically 1 is equal to RP. And from there, you know that P is equal to 1 by R. So this is exactly what we had derived last time, remember? But there we had relied on us actually knowing what is the formula for the infinite sum GP, right? Here, you do not have to know it. You just have to know that these basic finance concepts were enough. And also, actually, if you know that this term is finite, then you could have also done just basic algebraic manipulation and you could have found that out. Okay, so this is how it works. Let's look at, can we do something similar for deriving the formula for annuities, right? So now they are again back together, A and B, and then they don't remember how to sum up finite GP series as well, right? So last time they didn't know how to sum up infinite GP series. Now they don't even know how to sum up finite GP series. So they need to come up with a formula for annuity, right? And they understand what is the concept of annuity, right? So they understand that what they want is to figure out what is the present value of a stream of 1 unit per year starting next year and continuing for n years, right? So let's call this number that they are interested in figuring out AN. And because they are aware of the concept of present value, they know that AN is equal to 1 by 1 plus R plus 1 by 1 plus R squared, so on till 1 by 1 plus R to the power n. Okay. Now, student A, as usual, kind of like thinks about, okay, what happens if the payments come 1 year earlier than what would have been the present value? So he's thinking that we basically need to add 1 here, but because the payment is going to come till only for n years and you are beginning today, so you are not going to get the payment in the last year, right? So basically the adjustments need to be made on two sides. So he's thinking in terms of payment today, and starting from today is continuing for n years from today, right? So that means till year n minus 1. So this is the basically the present discounted value of that. And if he's comparing this expression that you see here with the expression for the annuity that he was interested in calculating, he observes that you have added 1 here, and you are kind of finishing at 1 by 1 plus R to the power n minus 1 instead of finishing at 1 plus R to the power n, right? So what it means is that you have added a 1, okay, but you have also subtracted this last term, which was here, which is no longer here, right? So compared to the payment beginning from 1 year later, if the payment begins from today, this is going to be the actual present value of that, right? So AN plus 1 minus 1 by 1 plus R to the power n. So that's the first thing that observes. And B, as usual, observes that, if you speed up the payment by a year, that's also equivalent to multiplying its present value by 1 plus R, right? So again, the same thing as before. So if you multiply the whole thing by 1 plus R, so what B observes is 1 plus R times AN is 1 by 1 plus 1 by 1 plus R till the power 1, till 1 by 1 plus R to the power n minus 1, right? Okay, so can they combine their knowledge to come up with an expression for AN? That's the question. So let's see how to do that here. So as I said, based on B's knowledge, this is the relationship. If you start from today and end in your year n minus 1, so you end up getting an expression which is 1 plus R times AN. And now we can equate this 1 plus R times AN to what A's observation was. So this must be equal to AN plus 1 minus 1 by 1 plus R to the power n. And now if you kind of like solve for this, so the two ANs cancel out. So you have got 1 minus 1 by 1 plus R to the power n is equal to R times AN. So AN is therefore expressed to this, right? Again, this is the same formula that we had for annuities last time, but that we had relied on using the finite GP series sum. And here you do not have to rely on that, right? Again, either you use the basic finance or you just kind of like understand how to manipulate these expressions and then kind of like get an expression for that, right? So hopefully this actually alternative way of deriving the formula for perpetuity and annuity gives you a bit more insight into how these processes work. Okay, so let's just look at our second question, which is where we are interested in figuring out how to kind of like use no arbitrage pricing to think about how to price assets such as oil, which deplete, right? So we are going to make out quite a lot of strong assumptions. The idea is just to kind of like highlight, how these principles that we are thinking of can be applied, rather than thinking about, okay, these are the most realistic picture of how to price oil, right? In reality, we know that oil is kind of like subject to various random shocks. both in supply side and demand side. So those are, of course, very important characteristics when we need to think about market for oil. But here, because our focus is on just highlighting how this no arbitrage pricing kind of relationship works, we are going to make assumptions that abstracts away from all those randomness, right? So we are going to assume that you have got oil. We know everything that is there about the demand for oil and the supply for oil today as well as in the future. And we think that this is something where this is a riskless asset, right? So all the perfect market assumptions that we have made also continue to hold. So in the sense that you do not have any large players, there's no disagreement and so on. And on top of that, we are imposing that there is no uncertainty. Okay. So let's see how we can use this to actually come up with an expression for the price of oil. Okay, so in the first part, let's assume that there is actually no cost to extract oil from the ground. We'll relax this assumption later and see what is the implication of that. We are interested in characterizing how does the price of oil change over time. Okay, so I have listed here a set of questions. You might want to pause the video at this point and just think about how you would have gone about answering these questions. And then you can compare the solution with what we state. Okay. All right. So let me just first go through the questions because they describe the setting. It's kind of broken down into multiple parts so that you can actually answer each of the questions with the information that is already kind of like given. But let's go over that once. So we are going to be assuming throughout that the interest rate is constant and is equal to R. Okay. So based on that, and based on the idea of no arbitrage pricing, can we first come up with a relationship between the price of oil in period T and T+1? Okay, that will be our first question. And we'll see that we can actually be able to come up with a rough answer to that. And that would actually tell us something about what's the rate at which we might expect the oil to grow by, the price of oil to grow by. Okay. After that, so that is a question about how the growth rate, but it does not tell us what will be the actual price level. So in order to answer that, we need to look a bit more detail into how does the market for oil work, in particular the demand side and supply side. So we are going to model these things very simply here. So we are going to assume that the demand for oil is going to be constant at D barrels per each year. And there is only a finite supply of S barrels in all in the world. Okay. So this is not S barrels per year. This is that total supply is just S barrels. Okay. So then in that case, if you have a constant demand and this is the total supply, we'll use that to figure out in how many years will this total supply of S barrels be exhausted. We are going to call that number of years as T. Okay. So once this oil supply is going to be exhausted, people will have to start using an alternative technology. And we are going to call that alternative technology LG. And that technology can actually produce oil or energy, let us say, once this natural oil kind of like runs out at a constant cost of C units per barrel. And it will actually be available to be used from this period T onwards. Okay. Now, assuming that this LG is a substitute for oil, right? Then we'll use that to actually see that what should be the price of oil when it is going to be kind of like being exhausted, right? So at year T, what should be the price of oil? We'll use that and all the information that we have kind of collected from this last few parts to actually come up with an expression for what should be the price of oil today as a function of this parameter C, which is the cost per unit of oil, or rather price per unit of oil of this LG technology, this parameter T, which is expressed in terms of D and S, and also the interest rate. And then we'll be able to kind of use this to think about some kind of like effect on what should be the effect of price of oil today if you have some changes in the model. Okay. So let's see how you would do that. So the first thing that we are going to be doing is we are going to be using this no arbitrage type of reasoning that we saw last time. And we are going to be thinking of it in the following, right? So here, the way to think about oil is that it's like any other asset. And because it's riskless, so it should be earning basically the same rate as money in the bank, right? So if you have got the money in the bank is earning a rate of R, which is what is given to us in the problem, then oil also basically needs to earn the same rate of return R, right? Why is that the case? Because if you had oil earning a higher rate of return, right, then basically you would not want to take out oil out of the ground, right? You would just prefer to keep it in the ground and wait to extract it later. But if enough people were thinking like that, what would happen is that the supply of oil at a particular time would shrink compared to the demand. And this would actually increase the price of oil up. And so that would kind of affect the rate of return, right? So if the price of oil is much higher now, then the rate of return needs to go down, right? So you will have automatically kind of forces pushing you towards the rate of return of oil becoming R, right? What would have happened if the oil in the our ground was earning a lower return compared to this R? Well, in that case, everybody would want to quickly pump out the oil, sell the oil, and get the money to actually put the money in the bank, right, and earn a higher return. Well, in that case, there would be too much supply of oil, and that would reduce the price of oil. And that reduction on the price of oil today is going to actually lead to a higher return, right? So again, you will have, if you have got that the oil's rate of return is less than R or more than R, there are automatically forces in the model that is going to push it back towards the rate of return R, right? So this is actually the same reasoning that we had seen last time, if you remember. Okay. So if you combine these two things, what it means is that basically the oil's rate of return is also R. And so therefore, from there, we know that the price of oil in period T plus 1 has to be equal to 1 plus R times the price of oil in period T, right? Why is that? Because if you now actually calculate PT plus 1 minus PT by PT based on this, you will see that that's equal to R, right? Okay, so what it means is that the growth rate of price of oil has to be equal to R, which is the same as the rate of return that the money in the bank was earning. Okay, so that's the answer to these first two questions in the first part, that no arbitrage condition tells you this is the relationship between the price of oil in the two periods, and the growth rate of oil is going to be equal to R. Okay, so the second question is actually pretty straightforward. So it's saying that suppose there is a constant demand at D barrels a year and total supply of S barrels, then how many years of oil are going to be left? Well, every year you have got basically D being exhausted and you have got total of S barrels. So therefore, oil is going to be running out in T years, where T is going to be given by this expression S by D, right? So D per year is the demand. So total demand in T years should be the same as the total amount of oil that is there. So dt is equal to S. So from there you get that T is equal to S by T, right? So you can see this makes sense, that the more the supply of oil, the further number of years it is going to last. So T will go up, and finally, higher the demand, okay, for a given level of supply of oil, quicker the oil will run out. So T will fall. Okay. All right. So let's now kind of think about what should be the price of oil at time T. Remember, at that point time T, there is this new technology that becomes available, and that price of that technology is C units per barrel. Okay. So what that means is that the price of oil at that point also has to be the same, because otherwise, if it is kind of like more, then people will just switch to this technology and will not want to buy oil, right? And there's no reason for it to be less, because there's no kind of like, competition will pull it up, right? So therefore, T years from now, oil must also sell at the same price as this other technology that is available. Otherwise, there won't be equilibrium in one of the two markets. Okay. So oil must sell for C units per barrel. Okay. So what we now know is the following. We know that the price of oil from today onwards, it's going to increase at a rate of R till it reaches at time T price equal to C, right? So we can actually use that to back up what must be the price of oil today, right? So remember, it's going at a rate of R. So therefore, P0 times 1 plus R to the power capital T, where T is this period where finally the oil is going to be exhausted and this other technology is going to become available, is given by C. So now I can write what is P0 in terms of all these parameters. So therefore, basically, we have that P0 is equal to C by 1 plus R to the power T. Okay. Now, the last two questions basically kind of like ask you to play around with some comparative static results, right? In the sense that suppose you change some of these parameters, what would be the effect? So the first question is, suppose there is some new unforeseen discovery of oil, right? So what that means is that there's going to be a higher value of S, right? And if S goes up, then from here we know that capital T is going to go up, right? And if we now look at this expression, if capital T goes up, the denominator goes up. And so therefore P0 goes down, right? So basically an unforeseen new discovery of oil is going to lead to an increase in S, which will lead to an increase in T. And this is going to lead to a decrease in P0. Okay. What happens on the other hand if you have got some technological breakthrough that decreases the value of C? So C, remember, is the cost or the price at which this new technology will lead to oil being sold at time period T. So if C goes down from here, we know that that will also lead to a value of C P0 also going down, right? Because these are kind of technologies which are linked through this pricing that we had discussed. Okay. All right. In the second question, we want to see what happens if we relax this assumption that we had made that oil can be costlessly pulled up from the ground, right? So suppose now that we put in that there is a cost of X per barrel to extract oil from the ground, and this cost is constant throughout. Okay. So basically, this cost is in actually real terms, as we'll see later. Okay. So now suppose we denote the price in period T by PT, and as before, we let R be the interest rate. So we want to basically come and see whether this relationship that we had derived, right, still continues to be the case, right? Okay. So this just tells you that, whenever we do this no arbitrage pricing, we have to take into account all these factors, right? So you have to be a bit careful in the reasoning, but the reasoning is consistent throughout. Okay. So let's see how the reasoning kind of works here. So the argument is broken down into different parts. So let's just go through it one by one. So suppose that a firm extracts a barrel of oil in period T, how much profit would it make? So remember, the firm can actually sell this oil at a price of PT, right? And it costs X to take out this oil from the ground. So therefore, profit at this point is PT minus X. Okay. What about profit in period T plus 1? So if it actually takes it out in T plus 1, then it's going to get PT plus 1. And again, the cost of barrel is still the same. So the profit is PT plus 1 minus X. Okay. Now, this is in terms of the profit at that period, right? But in order to make them comparable, we need to be looking at the present value of these profits, right? So the first thing to figure out is what's the present value of profits from extracting a barrel of oil in period T plus 1, and what's the present value of profits from extracting a barrel of oil in period T plus 1, right? So this is the value at that point. But if we want to compare it across different periods, we need to discount it in today's terms. And in order to do that, we'll do our usual procedure. So we will discount it by a factor of 1 plus R to the power T plus 1, right? Same way in which we do present value calculations. So this is the present value of the profits that you get if you extract oil in period T plus 1. And the present value of the profit that you get in period T is actually given by this expression that you see here, right? PT minus X divided by 1 plus R to the power T. Now, the fourth part is asking is that suppose the firm is actually willing to supply oil in each of these two periods, right? So what has to be true about the present value of these profits? Well, the present value of the profits have to be equal, right? If they are not equal, then basically the firm will supply oil in either one of the two periods, but not in both the periods, right? So you would supply oil in where it is most profitable for you, right? Okay. So therefore, that means is that the present value of the profits in the two periods must be the same. And from there, you end up getting this expression, right? Equating these two things. And you can actually take this 1 plus R to the power T plus 1 on this side. So if you do that, some terms cancel out. And then basically you end up getting that PT plus 1 is going to be equal to 1 plus RPT minus RX. Okay. So this is the relationship that is you're getting from this no arbitrage fact that, the profit has to be kind of equal. Otherwise, you will not be selling in both the periods, right? Okay. Finally, based on all of this, remember that we had calculated that the percentage growth rate of price rise in the between periods T and T plus 1 was actually equal to the interest rate in the first part. Is that still true here? So if we actually see this expression, and from there we look at what is the percentage change in price level. So that means that we want to calculate PT plus 1 minus PT by PT. If we do that here, you can do the algebra and you can show that this is going to be in basically that R minus XR by PT, right? How do you see that? So subtract PT. So you have got 1 times PT. So you're bringing that to the left hand side. And then basically you are dividing throughout by PT. So you end up getting this expression, right? So several things to note that if you had X equal to 0, which we had in part 1, you would have got that this is equal to basically R, right? Which is what we had here. But because X is something positive, that means that now the percentage increase in price is something less that you found in part 1, right? So the rate of return is now lower than R because now you have to take into account that there is an additional cost of working with this asset, right? So what this tells you is, again, to summarize, you have this notion of no arbitrage pricing, which we also use here, by the way, notice, at different places. But you have to be very careful about how you apply it, right? You cannot just blindly apply it to always say that this PT plus 1 minus PT by PT is equal to R, because there may be some costs specific to this asset, and then you have to incorporate in those costs when you apply the no arbitrage condition, right? So then you have to be a bit more careful and think about exactly what is the implication of the no arbitrage condition. So I hope this actually kind of like helped to make it clear about, how to work with this no arbitrage type of arguments. But of course, we'll see more and more examples later on, because this is such a fundamental concept in all of finance.